This is part 9 of lecture 11 of ELEC5300. In this part, I'll be talking about some applications of principal component analysis. One of the applications principal component analysis has been used in is in compression. So if we have a collection of handwritten digits which are all threes, this is an example of one of those digits. If we average all those digits together, these could be, let's say, rotated and slightly shifted versions of 3, I'll get something like this, which is kind of a blurry version of the 3. So this is kind of the average value of 3, and then other values of 3 are going to be kind of similar to this, except they're going to be shifted up or rotated or something like that. Now, I can construct any one of these guys by summing together all of the basis functions, where I choose the basis functions according to PCA so that they are the eigenvectors of the covariance matrix. So I could compute the covariance matrix from all the samples xn, and then find the eigenvectors and eigenvalues, and then plot the eigenvalues in order of decreasing value. Right, so these would be the largest eigenvalues down here, and these ones would be the smallest one, and this thing decreases smoothly because I've ordered them from largest to smallest. Now, if you remember, we had this term here that said, well, if we only take the mth, the eigenvectors up to m, right? Let's say, for example, that this was the value of m. If I'm interested in the error, what I would do is, let's say this is the error j. To get this point here at m, I would just look at all the eigenvectors, eigenvalues from this point all the way up to the end here. So if I want this one here, I just look at that. So this point here is obtained by summing all of these values here. And so obviously the lower I make m, the more I sum over, and the larger this reconstruction error becomes. So what I want is this reconstruction error to be small within a certain point, and so I can see here that if I choose, let's say, somewhere around this many, actually the error is not very big, but I can actually choose a certain error level, for example, like this, and then read off, well, how many principal components do I need to achieve that average squared error. And on the bottom here, I show you some examples of reconstructions of the original digit here, xn, right, by adding together the mean vector plus all these vectors here, which are the eigenvectors. And so one thing I can do is I can say, well, suppose we start adding together 1, 10, 50, or 250. What does the actual reconstruction look like? And that's shown down here, right? So obviously here, if I have something around 250 eigenvectors that I'm using in the reconstruction, then I'm going to do a pretty good job of reconstructing because the error is going to be pretty low. Right? So that's what's shown here, but obviously this one is not exactly the same as this one. There are some extra pixels here, for example, in this region and this region here, you can see a little bit. But if I have only a few, then I'm going to be very close to the mean. Right? But then as I add more and more, I'm going to get closer and closer. But you can see, for example, particularly around here, that even though this part inside here looks pretty good, I haven't been able to get rid of all this extra blue stuff around the 3. Okay. So the key idea here is that this reconstruction error then actually gives you an exact measure of what the mean squared error is. Actually, the principal components that I have here kind of give us an idea of what the kind of transformations there are So if you look at this one, for example, let's say this one here, right, what you can see is that this one is subtracting regions that are low, right, and adding regions that are higher, adding some blue stuff where the regions are higher. So if I added U2 to this mean, or a little bit of U2, what I would tend to do is subtract these guys and add some things on top. So that would, adding U2 would then kind of tend to shift the mean, this vector here, this mean vector up, or the position of the 3 up. Right. Conversely, this one seems like it's going to shift the 3 down a little bit. Right. This one seems like it's going to be shifting the 3 to the left a little bit, and this one seems to be executing something more like a rotation. Right. You can see it's going to add some stuff down here, add some stuff over here, subtract some stuff over here. So it seems like it's going to try to rotate it in the direction here, counterclockwise. Another application of PCA is in terms of trying to make the two variables, x1 and x2, to have kind of equal size, right? And also to fill out as much of the data space as possible. Right? So here I show you some data from what's called this Old Faithful data set. So the Old Faithful is a geyser. So a geyser is something that periodically shoots out water. So it's a hole in the ground. You know, something like this. It's got a little cone. And then there's some volcanic activity down here, and occasionally there's water sitting down inside here, and the steam builds up, and all of a sudden the water shoots out like this, right? Very high in the sky. And so there's one of these in the United States. It's called Old Faithful, and the plot here is really how long this geyser erupts for, so how long the duration of the geyser is, versus how long I have to wait between adjacent eruptions of the geyser. Right? So after this thing spews out its water, the water has to kind of rebuild, the pressure has to rebuild before it can shoot out again. And so it seems kind of intuitively clear that, well, the longer you wait, the more water has a chance to build up, and the longer the duration can be. So you see this positive correlation between the time that you wait here and how long the duration is. Now, if I want to make this thing to have similar units here, you can see that here the difference between the top and the bottom one is somewhere around 40 or 50, right? But here the difference between the leftmost one and the rightmost one is only about 2. Right? So one way we can equalize this is just to individually scale each variable by dividing by the standard deviation, subtracting the mean, and dividing by the standard deviation. That would put the mean value here at this point here 0, which would be right here. And it would make the extent in this direction and the extent in this direction about the same. But the problem, though, here is that there's still correlations between the data. You can see that there's a strong variation in this direction and not a very strong variation in this direction. And so that suggests then that actually, even though I'm only using the kind of the space between +2 and -2 in both of these directions, there's a lot of extra space over here and over here that's not being used. And so we can use PCA to kind of fix this problem, and the way we can do that is we can try to, instead of dividing in this direction and dividing in this direction, I can try to divide in this direction, the principal component direction, and in this direction. And what that would tend to do is kind of shrink this dimension and expand this direction, so I would fill out more of the data space. And so mathematically what we can say is, suppose that we take the new data, that's expressed as the original data minus the mean, so that's just going to subtract out the mean so that we're centered here at 0. And then I'm going to multiply by the eigenvectors transpose. And what that's going to do is it's going to project each of the differences here onto one of the principal components. So the first one of these might be the projection onto this component. The second one might be the projection onto this component. Right? Now, the first one is going to have a larger mean or larger variance than the second one because it's the first principal component. And so in order to correct for that difference in the variance for the first principal component versus the second one, I divide by the standard deviation for each principal component, which would be given by the diagonal matrix here, where the diagonal elements are the square root of the variance or the standard deviation. Now I can prove that this thing has a kind of spread all the data out by looking at the covariance matrix between y, which has 0 mean because I've subtracted the mean here, and itself, right? So that's the covariance matrix between y and itself. I substitute this expression in for y, so I get this up to here. So this part here you can see from the previous one is yn. And this part here is just the transpose. So I've just switched the order and taken the transpose of everything. Now if I move the summation inside all the way into here, then summing over this, which is the only part that depends on n, gives me the covariance matrix S. So I get this expression here, but now I know that U transpose times S times U is just equal to lambda, right? I can get that by just multiplying left by U transpose here, and noting that because this is orthonormal, U transpose times U is going to be equal to the identity matrix. So that's because it's orthonormal. So I replace this by lambda, and then I get a lambda to the minus 1/2 times lambda, which will give me another lambda to the 1/2, times another lambda to the minus 1/2 will just give me the identity matrix. Right, so that means that this is has a covariance where the ellipses are circular. And so that's why we call this sphering, right, or whitening the data, right? Because essentially what I've done is I have projected onto a set of axes which make the resulting variables uncorrelated, and then I've made sure that all of the variables have unit norm by dividing by or multiplying by lambda to the minus 1/2. And so this is the final distribution that I get after that, and you can see it's filling out much more of the data space, especially in comparison to this thing right here. The final thing I want to talk about is how do we deal with very, very high dimensional data sets. Now, if you recall, originally when I talked about this problem, I assumed that we had a lot of data. In other words, if we look at the data matrix, which I'm going to call X, that was very, very wide because I had a lot of data, right? So each one of these is a data matrix. This is n-dimensional here, right? And this is d-dimensional here. However, typically, because I'm using this for dimension reduction, I may be dealing with very, very high dimensional data. So you can see here maybe the dimension d for image processing might be on the order of 1 million or more, right? 10 million pixels in a typical digital camera. But then you don't take 10 million pictures, you only take a few hundred, let's say. So now if I have only 100 elements here, but the data matrix is, the data dimension is very long, then this thing here looks very different. In fact, this thing now, instead of being fat, becomes very, very narrow. So X now, the D is very long. I get these very long vectors, but I only have a very small n. Now, in fact, if I did find the covariance matrix, right, so assuming everything's 0, meaning the covariance matrix S would be X times X transpose, I would get a D by D matrix, right, because I'd have this long skinny thing here times this wide fat thing here. So this would be X and X transpose. So this would be D by D. Right? This is going to be a really, really big matrix, especially, you know, if D was 1,000,000 or even more. And this is going to be computationally complex because it scales as order of D cubed. So to handle this, we can say, well, instead of inverting this D by D matrix, if I can't find, if most of them are going to be ending up 0 anyways, because I only have n pieces of data, maybe I should try to invert a simpler matrix, right, that doesn't have me do all that extra work just to get a whole bunch of zeros. So we can do that using a little bit of a trick that will help us change the need to invert a D by D matrix or find the eigenvalues of a D by D matrix into finding the eigenvalues of an N by N matrix. So we're going to do the same thing here. We have this X, which is the data matrix, now again is D by N, right? So it's going to be this long skinny thing. And then when I get the covariance matrix here, this thing here is then S. I can get that just by taking X times X transpose. So that's going to give me the same thing I showed you before. It's going to give me that long skinny matrix here by this long skinny matrix here. Right? And when I do this times this, I'm going to get N times N, an n-dimensional matrix here by an n-dimensional matrix here, and then I'm going to have to do the averaging by dividing by n. Right, so this, actually I should have included this whole thing here as S. Right, so this whole thing here is S. So now what I can do though is take this whole thing and pre-multiply this whole thing by X transpose. So I get an X transpose here, and I get an X transpose here. So I get that, and now I can just regroup this. What I'm going to do is I'm going to say, hey, look at this. This thing here and this thing here I can call a new vector V. And so now I get another equation here. This looks like almost the same equation as this one. It's got X times U, but this one has X times V. But the key difference is that I've switched the order here. This is X times X transpose. Now this is X transpose times X. And so if I look at what is X transpose times X, X transpose is this long skinny thing. So this is X transpose. And this is X. Whereas the other case, this was X and this was X transpose. And so this is going to give me something in our D by D, right? But now because this is N here, this is N here, right? This is going to give me something in R N by N. So now this matrix here is going to be a much smaller matrix than this one over here. So I can find the eigenvectors much easier. Now the question though is, well, yeah, fine, you get the eigenvectors, you get these things v here, and now the v's here are going to be n-dimensional, but I still need to get the eigenvalues in the original data space. Right? And so the way I can do that is I can simply notice that if I take this expression here and then pre-multiply this by x, so I multiply by x here and I multiply by x here, I get this equation down here. And if I group this guy and this guy together, then I can say, hey, look, this is exactly the same equation as this. The only difference is that instead of a u here, I have x times v. Right? So actually u then is proportional to x times v, right? But I have to normalize it so that I get a unit length vector here. And so I can normalize that by dividing by this term here for each I. Finally, what I'd like to do is simply review the basic assumptions made by PCA. Right? So the first thing that's important to remember when we're dealing with PCA is that this is a linear transformation, right? And so it says that, well, the data lives in some subspace, but that's a linear subspace. It's all like a line or a plane. It can't be anything curved in the original data space. And that is probably not true in many cases. In some cases, it may be a good approximation, but the question may be, well, how could we find a nonlinear version of this? But that's beyond the scope of this class. It also assumes that basically the relationship between the measurement components are really completely captured by the mean and the variance, right? We never used anything else besides mean and variance in this analysis. And that's really only true if the data is jointly Gaussian, right? Because the Gaussian only depends on the mean and the variance. But if I have some other distribution, then higher order statistics may be important. The other thing is that somehow the important components that I'm most interested in, that I'm going to keep in the representation, are the ones that have large variance. Right? So this is essentially saying, well, the signal here is very large, and so I'm going to want to keep the components that are large, because hopefully those are the signals. But this is essentially an assumption about the signal to noise ratio being large. So if the signal to noise ratio is low, then actually the signal components could be very small compared to the noise components. And then by doing dimension reduction by PCA, I could be just focusing on the noise. And the final thing that's assumed by PCA that may not be true is that the important components making up this signal are orthogonal. And so if some of these guys are not satisfied, then that sets the stage for some variation of PCA called ICA, but we won't talk about that in this class.